quick lecture is about some different terms you can use to describe the distribution of your data. We're going to talk about standard normal distributions, then some of the differences you might see when you graph your own variables. Measures of central tendency are related to the shape of the distribution of your data, how the values for a given variable are clumped around some sort of midpoint and then spread out on either side, with the less common values above or below that midpoint. For example, on the left here you can see that most of the values for this variable are clustered around the mean at 0, and then there are fewer values spread out on the left and right. This is a normal distribution. Not normal because it's the most common or anything like that, but normal in its shape. It has a peak in the middle where the mean, median, and mode are identical or very close together, and then it has equal tails on each side. This distribution is symmetrical around the mean. Contrast this to the graph on the right, which shows a more uniform distribution of the blue bars. You can see that the bars and the red curve don't really match, because the bars are displaying a uniform distribution where responses were sort of spread equally over all possible values. Normal distributions are actually quite special. For a normal curve, the mean, median, and mode are all equal. Exactly half of the values fall on the left side of the distribution, and exactly half fall on the right side of the distribution. The area under the curve represents 100% probability. All possible outcomes fall under this curve somewhere. This means we can use the pieces of the curve to determine the probability of some outcome happening. For example, 68.2% of all possible outcomes will fall within one standard deviation of the mean. See these shaded areas? 34.1% on one side of the mean, 34.1% on the other, equals 68.2% within one standard deviation above or below the mean. So if the mean score on an exam was 70% and the standard deviation was 10%, and we knew the scores were normally distributed, we could predict that 68.2% of all test scores would be between 60% and 80%. That's one standard deviation below the mean and one standard deviation above. About 95% of all scores fall within two standard deviations above or below the mean, and 99% fall within three standard deviations of the mean. Normal distributions can come in different heights and widths, but they share the characteristics of being symmetrical around the mean, having an equal mean, median, and mode, and following that 68, 95, 99 standard normal model. The height and width of the curve just change the mean and standard deviation. For example, on the first three curves with solid lines, you can see that they all have the same mean of 80, but as they become flatter and wider, the standard deviation increases. 68% of all values still fall within that first standard deviation to either side of the mean. The two curves with dotted lines both have the same height and spread, as demonstrated by their same standard deviations, but the mean has shifted higher, further to the right side of our graph. These are all normal distributions. Your reading also provides you with two other terms for describing the dispersion of a distribution. One of them is platykurtosis, or a platykurtic distribution. You can remember this one by imagining a platypus. The platy part means flat or broad, so a platykurtic distribution has values that are quite evenly spread out. Compare the platykurtic distribution to leptokurtosis, or the leptokurtic distribution. If the platykurtic distribution is flat and broad, then maybe you can think of the leptokurtic distribution as leaping up. Lepto means narrow or thin, and you can see here that these distributions have values that tend to cluster together very tightly, with just a few much higher or lower values to each side in the tails of the curve. The normal distribution is really more of an idea or tool to use when thinking about probabilities. Many distributions are not very normal at all, especially in a field like criminology and criminal justice. Distributions are often skewed in one direction or another. Here we see a positively skewed distribution, where some unusually high positive values are pulling that tail to the right. The influence of these values on the mean means that it will be pulled higher than the median. A classic example of a positively skewed distribution is the age crime curve. One of the most robust statistical facts in criminal justice research is that criminal offending tends to peak in adolescence, like ages 18 to 24, and then drop off after that. But there is a small group of people who persist in criminal offending late into life, and these older offenders form the long positive tail toward the right side of this graph, where you can see we have some folks, men more so than women, who are committing offenses into their 50s and 60s. This would pull the mean age of offenders higher than what we really see as the peak on this graph, which is that 18 to 24 range. The reverse of that is the negatively skewed distribution, where a small number of very low values pulls the distribution towards the negative side of the graph, towards the left. These low values weigh heavily on the mean, which is sensitive to them, so it gets pulled down while the median remains about the same. An example of a negatively skewed distribution is age at death for Australian men. You can see that most Aussie men die of old age sometime in their 70s or 80s. That's a pretty good run. Few people live up into their 90s or to 100. But there are unfortunately cases of men dying very young, often from accidents or from violent crime, and so there's this long tail to the left, lower values where some men are dying in their teens and early 20s. These very low but uncommon values form a heavy tail on one side of this distribution. When we present the mean and median together, comparing these two numbers can actually give us a clue about the shape of the distribution. As I mentioned already, a standard normal curve is symmetrical around the mean, and the mean, median, and mode are all the same. But if a distribution is skewed, then the mean gets pulled higher or lower by those outlying extreme values, while the median stays the same. So if we look at this graph of annual household income in the US, we can see that the mode, the most common value, is around the 15 to 20,000 range, and the median is about 50,000. But we have a long tail to the right side. The distribution is positively skewed, pulled upwards by a small number of people at the far high end of the income distribution, households bringing in millions of dollars a year. Now, we don't know the mean, but we know that in distributions like this, it's going to be pulled higher. So this diagram of the mode, median, and mean on a positively skewed distribution actually fits pretty well. If you are presented with a median and a mean for a distribution, and the mean is higher than the median, you know you have a positively skewed distribution. If you're given a median and a mean, and the mean is lower than the median, you know the distribution is negatively skewed. One final set of descriptive words for a distribution uses the idea of the mode, the most commonly occurring value. Here we have three different distributions, and you can see they have a variety of peaks. So this one we call unimodal. It has one peak. Even though there are technically two bins at the same height here, we're more interested in the overall shape of a single peak with lower values to each side. In comparison, this distribution is bimodal, two peaks. I often think of this one when I think of academic departments. After the 2008 recession, a lot of universities stopped hiring new faculty for a little while. When they started hiring again, lots of departments ended up with a very bimodal distribution of employees, with some senior faculty who had been around before the recession, who were now older, then a big gap with no one in the middle, and then lots of new people at the lower end. And finally, we might say this distribution is multimodal, or that there are lots of peaks. We might think about the ages of people walking in graduation ceremonies as a multimodal distribution. If we think about everyone walking in any graduation ceremony in a given year, we'd have a peak around age 18 for high school grads, then probably another peak around 22 for college grads, then maybe another peak in the mid-20s or 30 for people who pursue grad degrees like law, medicine, PhDs, and so on. Of course, there are people who walk in these ceremonies at every possible age in between, but if we think about the most common values, we could definitely imagine that it's a multimodal distribution. And that's it. Now you have a handful of vocab terms for describing the shapes you might see in your data distributions.